My subject for today is the case for low aspect ratio personal aircraft, and some of you, I see a lot of familiar faces here, know I have been experimenting with vehicles like this one for a long time now, and I think there's a case to be made that this is a very good way to do a personal aircraft. So what I'm going to try to do today is to talk to you about a lot of the history of this, and then kind of the engineering that goes behind it, some of the concepts, and then near the end I'm going to give you an update on both. There's a replica of this airplane under construction, and on the new project, which is a two-place airplane designed around what were the light sport regulations until 3 days ago. But you know, the change in the regulations doesn't invalidate what would make this airplane really worth doing. I've been an airplane designer for a long time now, 45 plus years. I've worked on 28 different airframes that I can claim to have made a significant contribution to, that have made it into the air. And so this is just a little bit of the fun stuff I've worked on. But, you know, although I've made my living in the big airplane industry, my first love has always been general aviation. I got my pilot's license when I was 17. I just literally 2 weeks ago passed the 50th anniversary of my first solo. And yeah. It's kind of weird to get that old, but at least I can still fly, right? Yeah, I did it right. I took my 150 out for a couple of trips around the pattern, you know, so guess what? 50 years ago, I'd take a 150, couple of trips around the pattern, still doing it. But, you know, as a designer, I've been thinking in terms of what kind of airplane would private pilots really want, or should they want, should we create for them? And I'm trying to come up with the idea of a better airplane for the way we really fly. And you know, that's not an easy thing to do, because, you know, there's this old saying that conventional practice is not conventional because the old guys were stupid, it's conventional because it works. And so, you know, the wing body tail configuration works, and there's a huge amount of development, over 100 years of development in that configuration, and people have got it down pretty good. Just look around you, right? But, and I think, by the way, there's still a little bit that incremental, you know, refinement of the conventional airplane can still take us even further. But, you know, what appealed to me was looking to alternate approaches to see if we can do something considerably different that might have some meaningful advantages. So, you know, if you're trying to do a design, the first thing to figure out is, what am I trying to achieve? And so part of the game is to look at what do private pilots really buy. And there's this marvelous concept in economics called revealed preferences. And what a revealed preference is what you can learn by looking at how people really spend their money rather than what they say in focus groups. And so I found this statistic very interesting, and this is about 10 years old, but in half the time, well, Cessna, at the time I looked at this, had sold 37,000 172s. In roughly twice the time, Beechcraft sold 3,000 Bonanzas. Now you think about that. If someone said, okay, you've got infinite money and infinite pilot skill, which one would you like me to give you? Most people will take the Bonanza. But the thing is, what does the 172 do very well? It does very well at being an airplane that a pilot of very modest skill with moderate income can fly safely in a way that's valuable to them. It carries enough load to take some trips. You know, if you learned in a 150, you know, your 172 isn't going to be more than you can handle. And it's about as unsexy an airplane as you can find, but guess what? It is an airplane that works for a whole lot of people. So that tells us something about what the real private pilot really wants. Well, why is that? Well, let's take a look at how we really fly. You know, it's interesting because if you go back and look in the 50s and the 60s, even the companies making single-engine airplanes were trying to sell them as useful traveling machines. I mean, I own a Cessna 150. It's called a commuter. Okay? Not a trainer, a commuter. I don't know how I would ever commute in my 150, particularly since my office was right under the Los Angeles International Class Bravo. I mean, I don't think coming in every day in my 150 to go to work would have been very welcome. So we're basically making short average flights. We are usually sightseeing, VFR, $100 hamburger kind of missions. We're flying out of smaller airports, like my home airport in Independence is a 3,000-foot runway. Some of them are even smaller. Sport airplanes are flown by private pilots, and the reason I put that in there is because private pilots, that sets a level of pilot skill that the designer has to anticipate for being able to operate this airplane safely. And let's be honest with ourselves, if you're a private pilot, you're lucky to fly 50 hours a year, and most of that time you're not doing proficiency training. It's like, hey, I can go flying. I'm going to go get a hamburger. I'm going to go fly. I'm going to go have a look. Maybe I'll shoot a few landings. But you're not out there practicing departure stalls. You're not out there practicing forced landings. You know, we just don't. And so what that means is there's a level of proficiency we can reasonably expect from a private pilot. And cost is important. You're not making money with this airplane. So it's bought with discretionary income. So what does that mean? Well, I have to be able to afford it. If I can't buy it, it doesn't matter what the rest of the characteristics are, right? It has to be safe and safely operable with modest pilot skill. It has to have a comfortable cockpit environment, and that's for small values of comfortable. But there's got to be enough room to fit in the airplane. And, you know, it's interesting how, you know, I happen to own my second Cessna 150, and I remember when I bought my first one, which was about 30 years after I started flying in a 150, and my first reaction when I climbed into it was, damn, these things got smaller. You know, well, no. But, you know, it's a remarkably small cockpit, and there are other airplanes that are even tighter. And as a matter of fact, humans are getting bigger. And it has to have enough useful load so that you can put a person in each seat and enough fuel to do something. And that is turning into a real issue. And frankly, that was one of the real issues with the LSA regulations up till when Mosaic came out. And in fact, one of the very big wins for general aviation that they've changed the gross weight requirements, or I think we even removed them from Mosaic, because that 1320 pounds was quite restrictive. Because these are interesting numbers. When the 150, for example, was certified, FAR Part 23 specified a standard human as 170 pounds. Okay.
That was a long time ago.
Roger that. In any case, if you look right now, for American men age 35 to 39, the median weight is 194 pounds. That means 50% of guys in this country are heavier than that. 75th percentile is 227 pounds. Okay. If I take an airplane certified for 270-pound people and full fuel, and I put two 75th percentile guys in it, you cannot taxi to the runway without being in a fuel emergency. So it's interesting, if you take a look, useful load for two 75th percentile humans, 25 gallons of fuel, no baggage is just about 600 pounds. Okay, well, you know, most two-place airplanes don't have that much useful load. So you're already, you know, if you have big people, you're managing fuel. And personally, I believe this is one of the reasons why the Cessna Skycatcher failed in the marketplace. You know, it was an otherwise fine little airplane, but it had a useful load of 430 pounds, or 440 pounds within the LSA rules. Put two people in it, can't even put gas in it. Pretty much made this point already, but the real point here is that we buy private personal airplanes with discretionary income. It's the money we're spending to indulge ourselves. and operating it costs money, it doesn't make money, and that means you have to be able to afford the airplane. And I don't have this chart in this presentation anymore, but at one time I had a chart that compared the price of a top-of-the-line Cadillac with the price of a brand new 150. And it's really interesting because when the price of the airplane was within 25% of the price of that car, high-end but mass production luxury car, which I think is a pretty good indicator of the amount of discretionary income in the economy. Cessna was selling 1,000 airplanes a year. When the price got above about 140% of the Cadillac, the bottom fell out. And when I did that original chart in 2006, they didn't make 150s anymore, so I used the Diamond D820. The D820 cost 3 times what a Cadillac CTS cost. Guess why they're not selling a whole lot of them? Safety, very important, you know? So, two of my favorite quotes. Max Stanley was the chief test pilot of Northrop, who actually flew the original flying wings, and I love that the Piper Cub is the safest airplane in the world because it can just barely kill you. But you know, once you get airborne, you know, there's this lovely saying, takeoffs are optional, landings are mandatory. Once you're airborne, there's multiple possible flight incomes, you know. In gross categories, don't crash and crash. Good, bad. But you know, if you look at don't crash, we all hope for the normal arrival at where we were going. But you know, it gets progressively worse. But even if you get to the point where you can make a safe forced landing, even if it's an off-airport landing, get the airplane down on the ground, it's still a good day. Now, sometimes circumstance makes that not possible. And then we get progressive layers of bad. Well, as I know from personal experience, if you damage the airplane but not the people, after you get over being very sad and pissed off that you've damaged your airplane and you get over the adrenaline shock of, holy shit, I could have died, you realize it's still a good day. Then from there on, it gets progressively worse, hurting people, or eventually, if nobody walks away, that's bad. We don't want that. And one of the big things that determines that is a combination of speed and maintaining control of the airplane. And so this curve is derived from SAE data on crash survivability. And the vertical axis is the angle between the flight path and the ground when you arrive at the ground, and the horizontal axis is how fast you're going. Now, one of the numbers that blows my mind is out here. At somewhere around 78 knots, unless you're landing on a smooth surface, you're dead. Now, that doesn't sound that fast to us airplane people, right? But think about it. 78 knots is somewhere on the high side of 90 miles an hour. So an uncontrolled landing or descent or plop at 95 miles an hour, imagine doing that in your car where I disconnect the brakes and the steering and just toss you off the road randomly at 95 miles an hour. That's what that kind of accident is. Okay. At the other end of the spectrum, up here, you can see why some of these rules that we get imposed on really make sense. 45 knot stall speed, which was the LSA stall speed and the Euro microlate stall speed. Guess what? 90-degree impact is the threshold of doom, which means unless you fly into a brick wall, you'll probably survive. Now let's take a look, once again, FAR Part 23, 61 knot stall speed is somewhere in here, right? If I maintain control of the airplane and just glide into the ground at 61 knots, even if I don't flare, the impact angle is quite flat enough to be survivable. So once again, that makes sense. And you have to keep in mind that it's going to keep a little bit of margin above stall speed. So what I've done here, those vertical bars are various wing loadings in pounds per square foot, and about end up on approach speed. And once again, it makes a lot of sense, right? 10 pounds per square foot, Cessna 150-ish, light sport, pretty good. Heavier than 30 pounds per square foot, I'm flying an airplane that has to land on a smooth surface. So this kind of sets where do I want to be in terms of controllability and wing loading. it's interesting to me that even all these years later, with all the technology we've developed, stall spin accidents still kill people. And no matter how much we talk amongst ourselves about how that was dumb, I'm a better pilot than that, or we should train people better, once again, the revealed fact of the real world says it ain't going to happen. Sooner or later, everyone screws up, even the good pilots. And so what you want the airplane to have is safe, predictable flying qualities, and you want, when you get near the stall, for it to warn you, buffet, and not jump out from under you. And from the designer's viewpoint, the idea is that the airplane has to save the pilot because the pilot will not be able to save the airplane. Or you can't reliably expect the pilot to save the airplane. I mean, I have seen both, sadly, fatal stall spin accidents, and I've seen someone departure stall an airplane at 100 feet and recover at about 2 wheel diameters off the runway. So with all of this in mind, now we're setting out to what's a better airplane for the concept. What do we want to do? So, you know, we're reaching diminishing returns with the conventional wing body tail. And BRS is wonderful. I'm a huge fan of BRS as a safety item. Laminar flow composites, you know, you can do some really wonderful things if you look at some of the more modern airplanes on the field. You know, in terms of performance and everything else, you know, we've come a long way from my Cessna 150. But we can only go so far. I mean, if you look at safety, you have the discontinuous leading edge cuff, which has been around a long time. I know this in particular because I flew as a graduate student on one of the first flight tests of this in 1978. And, you know, the Coupe was a stall spin resistant airplane, and BRS definitely does a lot of safety. I mean, BRS right now, is their booth says they've had 457 lives saved by BRSs over the history. Cirrus alone has had over 100 successful deploys of the CAP system. So it's a marvelous thing, but it's not a fundamental paradigm shift. Similarly, you know, there's been a lot of interesting work done on reducing the cost of conventional airplanes. You know, you have beaded skins, and this airplane in the lower right is an airplane called the Amy Trojan, where they actually put the ribs on the outside to make it easier to rivet together. And there was symmetric airfoil, so all 4 wing skins were interchangeable. But what ended up happening is these airplanes were a little bit cheaper, but not enough to make a big difference, and the performance penalties you paid for the things you did for manufacturability made them slightly less desirable. So none of them were commercially successful. So we come to the conclusion that you can only get so far improving conventional airplanes. So now what? Well, now what is to channel your inner Monty Python. And now for something completely different. And so the idea was, what if we address this at the fundamental airplane architecture level rather than trying to simply infuse more technology into the classic configuration? And you know, that's a very fundamental design decision as you go. Do I continue? Because evolutionary design is amazing. If you take a look, for example, at a 787, it burns about 1/3 of the fuel per seat mile as a 707. Looks about the same. Nothing revolutionary there in terms of the configuration, or the architecture. But I said, you know, let's try something very different. And so the reason I put the Rand's S9 up there was not to attack my friend Randy's airplane, but because the S9 and my Facet Mobile had the same engine, a Rotax 503. And the Facet Mobile carries more load, flies faster, and lands slower than the S9. And oh, by the way, since it's a tube truss structure, kind of like the fuselage of the S9, about the time you're done building the fuselage of the S9, you're finished building the whole Facet Mobile, because the parts count. So taking the different approach, the standard Wing body tail configuration is kind of a monovariate approach, which means you look at aero and structures pretty much separately. And by the way, that's a virtue of that configuration, because one of the beautiful things about wing body tail is that you can decouple effects. You can move the wing back and forth to get it to balance. You can change the size of the tail. You can increase or decrease wingspan. There's lots of things you can do to adjust the design, which is why it was something that could be done successfully at a time when the slide rule was your most sophisticated calculator. As you start getting into these more integrated configurations, it gets harder, but it's worth doing. So my idea was, what if we take a multivariate approach where I'm taking structural weight and structural integration into account at the same time as I'm taking aero? Well, once again, every good engineer learns from the past, because an awful lot of smart people have done an awful lot of good work, and a lot of them have done us the great courtesy of publishing their work, and we can learn from it. You know, and one of my all-time heroes is Jack Northrop. I actually had this picture up as a poster on the wall of my college dorm room, which shows you what a total airplane geek I've been for my entire life, but nonetheless. So, what did Jack Northrop say? He said, our work has been dedicated to creating a type of airplane in which all the functions of a satisfactory flying machine are accommodated within the outline of the airfoil itself. So his idea was, you don't have anything extraneous. Every piece of the airplane is basically aerodynamically working for a living. And if you want to read an utterly brilliant paper, go find Jack Northrop's 1947 Wilbur Wright lecture to the Royal Aeronautical Society, where he lays it out in beautifully articulated technical detail, even to the point, and this just blows my mind, he understood what a modern, fully authority digital flight control system could do for you. He literally said, if I could move the center of gravity behind the aerodynamic center and have a sufficiently rapidly reacting autopilot to stabilize it, it would get these benefits. In 1947, he understood it completely. He didn't have the technology to do it, but he got it. You know, what a brilliant designer. But in any case, if you generalize Mr. Northrop's idea, you come up with the concept of what Richard Wood called an all-lifting configuration, which means the whole shape of the airplane or the vehicle lifts, generates lift. And as you can see from these, you can go all the way from aspect ratio, less than 1 on the X-24 to aspect ratio 7 or 8. And then, you know, in my professional life, I had the honor to be the chief aerodynamicist on the X-47, which is the airplane on your upper right. And just for a gee whiz number for you, that airplane has an aspect ratio of 4.5 and a max L over D of over 19. Yeah. A lot of fun to do that one. He also, Mr. Northrop also understood, and I won't read all of this stuff, but he made the fundamental point that the dimensions of the average human body may at sometimes be the limiting factor. He was doing big airplanes, bombers, so, you know, the canopy could be a little bump on the top, and the bump was only big enough to give the pilot some visibility, and very small relative to the size of the airplane. Great, it's got a 172-foot wingspan. Now, I want to make an airplane to carry 2 people. So, we have this dilemma. The classic flying wing is an extremely efficient configuration, but people don't scale. So as I start shrinking that airplane, I get to a minimum root chord, which is somewhere in the neighborhood of 16 to 18 feet, depending on how aggressive you want to be on airflow thickness. And you can't get shorter than that, you know, in a blended wing configuration, or the airflow will separate over the airfoil. Okay, well, that's a problem if I'm simply trying to build like a scaled down Northrop flying wing. Because if I were to take the plan form of the B-49 or the N9M, which was the 1/3 scale test airplane they built, to that 17.5-foot root chord, it's got an 80-foot span and 905 square feet of wing area. That's a little big for a 2-seat airplane. So the idea then becomes, what if I keep the root chord the same and start cutting the wingtips off until I get down to a reasonable wing area? And then you end up with something that looks, well, like the Facetmobile. But the question then becomes, okay, now I've gotten to a very low aspect ratio configuration. Does that still retain the advantages of a flying wing? And in some ways, yes, it does. And once again, look to history. part of what got me going on this was I found in history there were several quite low aspect ratio airplanes that had performance far better than conventional wisdom said they should. I mean, the Dyke Delta was one of my great inspirations. I still have my July 1972 copy of Air Progress with the cover of Dyke Delta on the cover. You know, and 555 Alpha is now in the EAA Museum. It's John Dyke's prototype. And I'm very happy to have, in later years, met John Dyke and gotten to know him because he's a real inspiration to me. But even earlier, there was this airplane called the Arup, and then, of course, there's one of my all-time favorite airplanes, which is the Avro Vulcan, which has aspect ratio about 3.5. And at the time of the Falklands War, when the Vulcans flew the missions where they bombed Port Stanley, it was the longest range combat mission ever flown within the atmosphere. Now, granted, the aerial refueled a bunch of times, but that record wasn't broken until the B-2s got sent into the Balkans about 20 years later. But fabulous airplane. And then, you know, there have been a lot of interesting history of other airplanes. There's a gentleman in Australia named David Rowe who keeps building these, and he's on UFO number 4 at this point. And they fly very well. There's video out there. And then Milt Hatfield did, you know, who actually flew the original Arabs, built the little birds as lights, as ultralights, and Bart Verhees in Belgium is flying the Verhees Delta. You know, so there's been a lot of work that says, hey, you know, low aspect ratio can work pretty well. So I started to think about why, because I found it interesting. Why does this work? Well, here's why. It's lightweight. It's intrinsically, the wings are short, they're thick, the bending moments are low, the loads are distributed. Very lightweight. Just as a G-Whiz number, the original Facetmobile weighed 370 pounds empty on the ramp, and that included the BRS and all of the avionics. Now, what was the avionics? It was an ICOM handheld on a clip, but that was in the 370 pounds. Structure can be very simple. One of the interesting things about low aspect ratio wings, if you design them right, is they will go to very high angle of attack, and they have a very flat top lift curve. So they don't have the classic stall. The other interesting thing about them is because the root chord is so long, they have a very wide center of gravity range. Because, you know, the allowable center of gravity range tends to be a function of percent chord. Well, on the Facetmobile, the mean aerodynamic chord is 14 feet. So it's got a 15-inch allowable center of gravity range. You know, which means it's very tolerant of varying loadings, which is nice. And then, you know, it's got a roomy cabin, just because there's all that volume. And the other thing that's neat about it is you have crush space in every direction. So you're sitting in the center of this cage. If you have to hit something, there's lots of stuff to absorb the energy between you and the thing. So, nice theory. How does it work in practice? Well, so the first project was this airplane. This picture was taken in 1994. That's the October 94 cover. We had it out in front of the Brown Arch. I flew it here from California. And I'll tell you, folks, as an EAAer, it doesn't get any better than that. You know, to bring your own original design here and get the cover of Sport Aviation, you know, it was almost 30 years ago, and it still chokes me up to think about it. So it's a very cool experience. But, you know, what were we trying to accomplish? Well, the first thing is, you know, I had all this theory, and I was drawing it, and I really was thinking well of myself. And then, in about 1988, 1989, I was walking up the flight line here at Oshkosh, and I came upon the most god-awful thing sitting out there. It was a little biplane. It was kind of dirty, a little bit lumpy. It had a canopy made of Lexan, literally held together with sheet metal screws. And I'm standing there thinking uncharitable thoughts about this person's airplane. And then I realized, yeah, but he finished his, and he flew it here, and yours is a sketch on a quad pad. Get real, right? And so I wanted to do all this exploration, and I'm very happy to report that we succeeded in both of those 2 bullets on the bottom. We won the Dead Grass Award for 1994, no question. I definitely did get a bunch of UFO reports, and there's one story a friend of mine told me from the initial flight test of the Facet Mobile. I was orbiting over Chino Airport, and I was throttled back, so not much faster than the road cars, right? And there's a guy on the airport perimeter road in a pickup truck, and my friend was following him, and apparently the guy's had his head out the window, and he's looking at this thing going overhead, and it was painted black on bottom, so it's like, oh, first sighting of Aurora, except it's awfully slow, right? Well, so he's watching this thing, and then, I got to the end of my orbit, and I turned toward the airport, and he turned toward the airport, and the road didn't turn toward the airport. And so he ended up in the ditch with, Chino is a dairy preserve, so he ended up in the ditch with stuff. But, and when I flew it here, I was staying low altitude most of the way following the highways. I wish I'd had a CB radio back in those days just to hear what people were saying. But I got a few reports from friends along the way. Okay, this is a question everybody asks, and it's real simple. It has nothing to do with the F-117. As a matter of fact, when I was designing the Facet Mobile, the F-117 hadn't gone public yet, which, given the industry I work in, was very lucky for me. Because, if I had known about the 117, I wouldn't have been allowed to build this airplane. As it is, once when I came back to Northrop, I was building this airplane working for another company. I was very careful to make full disclosure of what they're doing. And they were actually very cool with it. The next question people always ask is, doesn't the airflow separate over the facets? Well, I was fortunate enough to get a wind tunnel test, and if you look at the tufts here, you can see that, no, it doesn't. We were, on this particular shot, we were experimenting with vortex generators at the canopy top. Turns out it didn't need them in the real world. So all the way out at 30 degrees angle of attack, which is on your right, the only separation, if you look very carefully, just inboard of the vertical fins a little bit. And actually, if you try to take the airplane to a high angle of attack, you can hear that happen. You can hear a little buffeting, and it sounds like someone's tapping on one of the verticals. But even at full aft stick, the airplane is completely stable, completely controllable. It just sinks at about 1,000 feet a minute. And you can still control it laterally with the stick, which can be great fun when you're out playing, because you can pull the high angle of attack and roll. You stop in midair almost. It's got no energy, but nonetheless, fun airplane to fly. About 180 degrees a second roll rate, among other things. And so it was time to bring it to Oshkosh. So this was 1994, day one, about 2 hours after I brought the airplane in. This was one day later when I was out in the flyby pattern. Back in those days, you could still do flybys. And you will notice that, once again, that you have the perfect plan form of the airplane in the grass already, including, if you look very carefully, you can see the propeller. By the time we left at the end of the show, that trench around the airplane was about 3 inches deep. People were interested. It was very cool. But, what did we achieve in terms of, other than, okay, we wowed them. Great. By the way, one other thing with Oshkosh is we got so tired of answering the does it fly question that we put on the prop card, this aircraft was flown here from Chino, California. They kept asking. But we could still point them and say, go read the prop card and get back to me, But what did we actually achieve with this airplane? Real numbers, okay? It weighed 370 pounds empty, flew at a max gross of 740 pounds. And on 46 horsepower, Rotax 503, it would do a little over 100 knots. And that was without wheel pants. And my block speed, counting, brake release to shut down for all of the legs, flying it here from Chino, which is 2,500 miles, was 77 knots. So I consider that to be a reasonable proof of the viability of the concept. And then I add that I was about a 200-hour Cessna driver when I started, and the airplane never once scared me in terms of its flying qualities. It was an easy airplane to fly. So, the intent was to go on to a two-place. And this was an airplane called FMX-5. This is circa 1995. And once again, got as far as wind tunnel test and a flying RC model with this. Life intervened in some ways, and I didn't at the time have the resources to build this airplane. But some of the wind tunnel data is really interesting because, once again, this is lift versus angle of attack. And you can see we approach at about 15 degrees angle of attack at about 50 knots. Max lift is at 35 degrees angle of attack. So that means that on approach, I've got a 20-degree angle of attack margin to max lift. And oh, by the way, the lift curve's flat, so if I go beyond that, who cares? Just to put that in perspective, a typical light airplane like we normally fly cruises at 2 or 3 degrees angle of attack and stalls at about 15. And we approach it like 12 or 13. So we normally are used to approaching with maybe a 3 to 5 degree maximum angle of attack margin. This has this much more. The other thing that is really cool about it is this is pitching moment versus angle of attack. This is nose up, this is nose down. And you'll see right about 25 degrees angle of attack, there's a very strong nose down brake. And so even with full aft stick, you can't trim the airplane above about 25 degrees. So it naturally self-angle of attack limits in very much the same way a canard does. For different reasons. There's an aerodynamic shift. It's not that we're getting partial stall, we're getting vortices developing and the centroid of the vortex lift is moving aft. But and it's not that we're blanking the elevons because I still have good roll control. But what it means is you literally can't trim the airplane beyond max lift. And so if we go back to the curve of doom, think about this. Even in my 150, if I have an engine failure and I maintain a little speed, I'm going fast enough to hurt me if I don't maintain real good control. In the low aspect ratio airplane, maintaining my margin above minimum speed, I'm coming in very flat at about 45 knots because I maintain lateral control, I maintain pitch control. It's not going to jump out from under me. And in some respects, I think that characteristic may be one of the reasons why I'm here to give you this talk today, because the reason the original Phasmobile is no longer flying is I had an engine failure at about 600 feet. And I was able to put it down upright, slow, and walk away from it. So at some point, this attracted the attention of NASA, and Mark Moore gave us a contract to look into this as a low-cost personal air vehicle experiment. You can see up there, that's the NASA citation for the NASA document. It's out there on the NASA database. You can also download our final report from my website, which is wainfan.co. And wainfan.co, by the way, not .com. So we were looking at a lot of interesting things here using automated manufacturing. It was mostly oriented toward cost. And, the conclusion was you could significantly reduce cost while maintaining these very interesting characteristics. So, okay, it works. Why? Because, an engineer's normal response to a set of data is, okay, I see the airplane, I see you got these real numbers, I believe that you measured that, but why did it do that? Because once again, conventional wisdom says that low aspect ratio is inefficient. But is it really? Well, first question is, what is efficient? And so one way to look at this is that an airplane is a machine designed to transport payload. I'm taking a blob of stuff and moving it from here to there. So what do I care about? I care about how much fuel, how much energy it takes to move the payload. Everything else is overhead. the energy it takes to move the airplane is overhead. Unless I'm a sailplane, unless I'm doing sailplane competition, right? Because it's tare weight. It's like moving the empty box from here to there, right? Well, what goes into this? It's not just aero. The aerodynamicist cares about lift to drag ratio. In the structures world, it's questioned, what's the structural weight fraction? How much dead weight am I carrying just to keep the airplane together, right? And then one of my laws of aerodynamics is it's always propulsion's fault. And so the engine-specific fuel consumption is another issue. Not going to address the propulsion side because the work I'm doing is on vehicle architecture and I can basically buy the same engine as everyone else, right? But, so the airplane figure of merit is not lift to drag ratio, it's payload to drag ratio. And that's a very interesting number because when you go through all the math, and I won't go through the whole derivation, what you discover is that payload to drag ratio is simply the payload fraction times the lift to drag ratio. So what percent of that load is useful load or payload. What's really cool about this is it lets you compare dissimilar configurations for efficiency, and it lets you explicitly trade structural efficiency against aerodynamic efficiency. So the idea is if I'm getting higher aspect ratio, I'm improving my aerodynamic efficiency while I'm making my wing heavier. Am I coming out ahead or behind on this number? If I go the other way, I make the airplane lighter at the cost of L over D. Which way am I coming? But this is the figure of merit you're looking at. And I did not invent this, of course. It was originally postulated, though not in quite that clean a form. There's this wonderful paper in the Journal of the Royal Aeronautical Society by a gentleman named G.H. Lee, who did a lot of amazing work. But he postulated the idea of this, which was called an OG Aerobus. To me, it looks like the Pudgy Plane's interpretation of the Concorde. But basically, by the way, oddly enough, OG Aerobus, this drawing is actually the very beginning of Airbus Industries. You know, because the Europeans were putting forth originally the idea of standing up a company to make a short-haul airliner for intra-Europe travel. But what Lee found out was very interesting because they had originally started out with a flying wing. And they did their studies and they found, hey, it ain't any better than a conventional airplane, what the heck? And so he started doing in his paper the exact thing that I showed you of starting to cut the wingtips off. And the more he cut the wingtips off, the better it got. And he went, what the heck? In a very British way, which I won't try to imitate, of course. But, and eventually he figured out that what it was this trade of weight against L over D. And so he took the next step and said, okay, instead of a flying wing with its wingtips sawed off, what if we blend it? And the paper really beautifully articulates this philosophy. And it got as far as wind tunnel testing, but the combination of the fact that it was really radical and the fact that Handley Page went bankrupt meant that when Airbus finally stood up, they did a much more conventional airplane. So let's take a look at those components that go into transport efficiency. It's payload fraction and lift to drag ratio. Well, let's look at weights first. These are all, every dot is a real airplane. And this is the useful load as a function of gross weight. Now what's interesting is all of these airplanes are low aspect ratio blended airplanes. Dyke Delta, Hatfield's Little Bird, Facet Mobile. And these are all wing body tail airplanes. But you can see, interestingly enough, typically in the classical light airplane world, we're at aspect ratio 6 or 7. I'm down here at 1 to 1.5. So for a given mass of payload, we're taking a lot less airplane. Now the first thing that means is it's cheaper because I'm just buying less pounds of stuff. Second thing is, okay, I bought a big structural efficiency to go into that transport efficiency. Now let's take a look at the lift to drag ratio side of things. Once again, and this is as much math as I'm going to subject you to, I promise. It turns out the drag ratio, what's really interesting is when you calculate it, the chord drops out. Aspect ratio doesn't matter. What matters is span span efficiency, and wetted area. And then skin friction coefficient, which is a measure of how smooth it is. So if we look into components of that, first thing that's interesting is a low aspect ratio, all lifting airplane has a very high span efficiency because it's got a nearly elliptical span load and it doesn't have a wing root junction to mess it up. Span efficiency of a good wing airplane is in the 75 to 80% range. Really good, maybe 85%. I flight tested one low wing production airplane, did a performance flight test, and I measured a span efficiency of 57%, which I found quite horrifying. But nonetheless, this is from the FMX 5 wind tunnel test that I showed you without the tip fins, just the hull. And you can see the green dots are a span efficiency 0.9 polar. So it has a span efficiency in excess of 0.9. Now, if we're looking at the skin friction coefficient, we have another neat trick. That is, skin friction coefficient is a function of Reynolds number. Reynolds number gets bigger as chord gets bigger. As Reynolds number gets bigger, skin friction coefficient goes down. So if I have a mean chord of 14 feet versus 4, it turns out that my average skin friction coefficient is 18 to 20% lower. Which means that even though I have a bit more wetted area, I pay 20% less per square foot. And you add those combinations together, and they improve the L over D of the low aspect ratio airplane just enough to offset the slightly shorter span and the slightly greater wing area, wetted area, and you retain the structural weight advantage. So once again, does this sound great theory? How does it work in practice? Well, we have data, right? So comparing Cessna 150 to the Facetmobile, aspect ratio 7 versus aspect ratio 1. If we first of all look at, on the top curve, it's lift to drag ratio as a function of airspeed. You look at that curve, the aero guy says, we're done. This sucks. Now I take the payload fraction into account and look at that. At cruise, the curves cross. And the aspect ratio 1 airplane actually has a slightly better transport efficiency than the aspect ratio 7 airplane. Now, granted, neither one of them was particularly sophisticated in terms of skin friction coefficient. If I built a laminar flow 150, this would change. But Facetmobile was lower than optimum low aspect ratio because, once again, that scaling thing, it's 18 feet long, single-seat airplane. On the two-place I'm building, I left it at 18 feet, pushed the span out to about 22 feet, the aspect ratio up to 1.8 or 1.9. My experiments say that the real sweet spot is in the aspect ratio 1.5 to 2 range, somewhere. So, the original FMX5 was created before the LSA rules. The LSA rules came along, and I understand they've changed, so this chart is a little out of date, but still, this is the thinking. So I said, I want to design, since I never built FMX5, I'm continuing to evolve the design. I'm going to aim it at the LSA roughly gross weight. By the way, that turns out to have more than enough useful load to do what I want to do. And this led to an airplane that I'm now calling FMX7 or Bat Ray. And this is what it looks like. This is a wind tunnel model of it. And I was fortunate enough, through my association with Cal Poly Pomona University, to get 2 really good wind tunnel tests of this thing. But this is what I am building right now in Independence. So in any case, we all know what the old rules were, and that 1320 gross weight was a severe limiter. And as I said earlier, even without that, I want at least 600 pounds of useful load in a useful two-place airplane in today's world. So, built-in RC model. I love what you can do in today's world with little autopilots and all that. We were data logging off of this model, and I actually was able to cross-check the wind tunnel data with it. It flew beautifully. Notice this has an earlier fin configuration, which is the simple twin verticals, which it flew fine. The only reason I was able to do the inverted V-tail at all was because I was able to do the wind tunnel test and get good quantitative. And then I was working with students at Cal Poly Pomona, so they did some CFD work on it. And then, as I said, we got a pretty good wind tunnel test. We actually did almost 60 hours of testing on this. So I was able to test all kinds of interesting configurations. 60 hours sounds like a lot of testing, but you know what the last words of every single wind tunnel test in the history of man is? Can I have one more run? The aero guy always wants one more run. And here's a look at the tuft, so you can see they're pretty happy here. We're at, there's a little bit of something happening right here on the back of the canopy. And if you look very carefully, the sting shroud is perturbing the flow a little bit, but nonetheless, nice attached flow. And then, as I said, we developed the inverted V-tail configuration, which is going to let me use bias of the rudders for pitch trim. So here's what the lift curves on this one look like. And they're even nicer than FMX5 because, as you can see, we've got a max lift coefficient of just over 1 and this beautiful flat top lift curve. And I think this goes out to like 35 or 37 degrees, which is as far as the wind tunnel support system could go. So we literally could not pitch the model up high enough in the wind tunnel to find max lift. But once again, do I care? Not really. Where am I going to be approaching 12 degrees angle of attack? And it retains this nice gentle nose down brake pitching moment characteristic at high angle of attack that I showed you for FMX5. So, okay, great. The aero part works. It works well. What about weight? Well, I did some weight estimates, and of course, I won't really know until I put the airplane on the scale. But once again, I had lots of data to estimate, so I'm going to be showing you some predicted performance, and this is the basis of all of that. From the weights, first of all, I have the actual physical weights of the original airplane. I have correlation with other low aspect ratio airplanes because I happen to have an accurate weight breakdown of the Dyke Delta and a couple of others. And then from the aerodynamics side, I've got wind tunnel data and what we measured in flight with the Facet Mobile. So I used 3 methods to estimate the weight, and depending on how optimistic I am, I can predict an empty weight all the way as low as 516 pounds and as heavy as 650. You know, some of them were like incrementing off the Dyke Delta, some were building up off of the Facet Mobile. What was the statistical weight correlation to that chart I showed you earlier? And so for design, I chose the heaviest weight estimate, which is 650 pounds. But think about that. If I can get that airplane on the ramp at 650 pounds, I will have over 670 pounds of useful load within the 1320. I'm actually designing it to 1400. So I think I got a pretty good shot at having close to 700 pounds of useful load in a 120 horsepower 2-seat airplane. I think that's worth doing if we can pull it off. Even if I'm 50 pounds overweight, we're probably pretty good. So if you compare that to existing airplanes, it's interesting because you look at the Cessna 150, it's got 515 pounds of useful load, and you're buying 1,100 pounds of airplane. You look at the Diamond, 580 pounds of useful load, 1,700 plus pounds of airplane. You look at Bat Ray, 670 pounds of useful load, and I'm only buying 650 pounds of airplane. Now, that's not quite as dramatic as it sounds, because guess what? The engine for the 2 airplanes costs the same. So do the avionics. But in terms of the structure, there's savings. And what's interesting here, this is a stacked bar chart that just shows what percentage of the airplane is empty weight and what percentage is useful load for the Diamond and the Bat Ray. And you can see the green is the useful load and the gray or blue is the empty weight. So you can see that with the lower aspect ratio approach, you're getting a much bigger load fraction. So once again, let's go through some of these comparisons. Well, the DA-20 is a modern laminar flow airplane. Once again, the aero guy says, why are you bothering with this low aspect ratio airplane? But here's the interesting thing. Now, take a look at the orange curve, which is the Bat Ray, compared to the Cessna. Much higher max L over D, slightly L over D. But there's another interesting characteristic, and that is that low aspect ratio airplanes hit their max lift to drag ratio at higher speeds than high aspect ratio airplanes. So even if you have the same max L over D in terms of cruise, it's actually biased toward cruise. So same max L over D, you're getting a 20 to 30% better L over D at cruise. So when you now go to the actual weights and you take a look at the actual power required to fly, first thing you see is how far we've come from the Cessna. Not that I don't love my 150. But what's interesting is if you compare the Diamond to the Bat Ray, in spite of the huge difference in L over D, up in the cruise speed range, they don't take almost exactly the same power. And the Diamond version that I did this from was a slightly earlier version with a lower useful load. And so when you take the useful load into account, you end up with a higher transport efficiency for the Bat Ray. And now this is compared to a modern composite laminar flow airplane. Now the thing I would dearly love to do is to see what I could do if I went from tube and rag that I can build in my hangar to a really beautifully smoothed out smoothmobile. See how much more because I think I'm taking a 5 to 10% parasite drag penalty for the fast setting. The other place where things get really interesting is power to weight ratio. Remember, I'm carrying the same payload, I have the same horsepower, several hundred pounds difference in gross weight. What does that do to climb? Well, a lot. Here's rate of climb as a function of altitude. Now, these are book numbers. I have never, in my life of operating Cessna 150s, seen 700 feet per minute sustained. I love my 150, but no, it won't do that. But that's what the book says. This is what the Diamond book says. This is what my calculations say for Bat Ray. So, and oh, by the way, it'll be climbing at 90 knots, not 70. So it means in terms of cruise climb, it'll be very nice. And that's because of that shift of max L over D. Same thing on takeoff. I've got 5 pound per square foot wing loading on Bat Ray, 10-ish on a 150, about 12, 13 on the Diamond. Power to weight also affects acceleration, right? Same power, lighter weight, you accelerate faster. And distance goes as the square of the acceleration. And what that does to takeoff is amazing. This is takeoff distance. Bat Ray, about 400-foot takeoff roll. Phasmobile was about that. Hits 50 feet at about 600, 650 feet from brake release. The Cessna driver is going to be rolling another 100 feet past that 50-foot obstacle that the Bat Ray just cleared. And when the Cessna gets to 50 feet, the Diamond pilot is just thinking of rotating. And this is the effect of power to weight ratio and wing loading. Because with the low aspect ratio airplane, with the low wing loading, I'm taking off a few knots slower, but because I'm lighter, I accelerate faster. On the other end, even though the max lift coefficient of the low aspect ratio airplane isn't that high, its wing loading is really low, so my minimum airspeed is lower, not quite stall speed because it mushes, so I can approach about 5 knots slower. From a safety viewpoint, once again, the energy I got to dissipate goes as speed squared. Also for landing distance. The slower I land, the less distance. And so, you know, getting into aircraft that were nominally legal within light sport as it was until Mosaic, you can see the Cessna Skycatcher at 486 pounds of useful load. This is a big problem when you're trying to run a training thing, because even if I have average-sized people, I've got an hour plus reserve fuel legally, which means I have to refuel that airplane after every cycle. And that's killer, trying to run. And heavy student, I tell, go someplace else. Flight design actually did remarkably well with the CTLS. It's a beautifully designed airplane. But we still end up better with Bat Ray, and oh, by the way, twice the rate of climb. Cabin is 84 inches wide, and the luggage compartment is roughly twice the size. Now, the only danger of that is you can overload it. You know, I got that much volume. So this is roughly what the performance will be. This is what the structure looks like, all tube. And so that's what the project's about. I'm going to give you a brief update on what's happening on 2 projects. And then if we have a few minutes, I'll be opening it up for questions. So, as a lot of you know, a gentleman named Bob Engel is building a replica of the original Facetmobile in Independence. And he's been working on it for a while. And so here's a few pictures of that when it was naked. And this is roughly where it is now. This is about a month ago. Since this picture was taken, Bob has converted that cardboard cowling to metal. He's plumbing the oil cooler as we speak. And if fate is kind, we're within probably about a month to 6 weeks of being ready for taxi test. And if you look very carefully, you can see the wingtip of the bat ray. So these 2 projects are side by side, and of course the RC model. And this is all in the EA Chapter 292 hangar in Independence, Oregon. And so this is what's happening on Bat Ray. One of the really cool things that we're doing in Independence is we've got a member of our chapter named Robert Haynes, who is a brilliant mechanical and manufacturing engineer. And Robert has in his garage a homemade 3-axis NC system and his own homemade software. I can give him the center line of all the tubes and how many rivets I need at each junction. And his software will generate all of the copes and all of the gussets, and he will cut it all, and it comes off the machine with the Cleco holes. Everything fits perfectly, and I do not have to do it with bandsaw and file. Thank God. Just to give you an idea on Bat Ray, and I'll show you a few more pictures. I got the parts from Robert. We Clecoed it all up. Remember, it's a 19-foot long airplane. There's 5 transverse tubes on the bottom. Clecoed it up, sitting on sawhorses. Put my digital level on those tubes. All 5 tubes are parallel to within less than 1/10 of a degree. Straight off the machine. Gotta love it. And so this is one of the outer panels. And then center section. And this is the state of the airplane right now. We're just about to do the wing mate to get the wing attach fittings properly drilled and reamed so everything's lined up. One of the biggest challenges actually in engineering this airplane has been putting those manufacturing brakes in it so that it's 3 sections instead of 1. Because the original Facetmobile was 15 feet span, 19 feet long, single piece. Well, when I had to truck it from where I had my forced landing, that was a bit of a thing. Now, you add another 7 or 8 feet of wingspan, it ain't happening. And so it meant, you ended up having to double up this rib and do all those attach fittings. I'm probably taking about a 25-pound weight hit when I take the fittings and the bolts and all of that into account just to have that capability. It'll also make it a heck of a lot easier to cover. Because covering the original airplane, we literally hung it from the ceiling on its side, and it was like painting a billboard. We were on ladders. I don't want to do that again. So this is where we are at. In the foreground, you can see the beautiful set of landing gear Robbie Grove built for me. And when I get back after Airventure, sometime in the next 2 weeks, we'll probably be doing that preliminary wing mate. And then I am resolved to touch this project every day until it flies. So, final thoughts. I think I got something here that could be a pretty cool airplane for all of us. I've just spent the last hour articulating why I think so I'm not going to go through much of a summation beyond that. And with that, I think we've got about 10 minutes before the next speaker is supposed to be here. So thanks very much for your attention and for being with me on this marvelously hot day. And let me open it up for some questions. All right.